These final videos, we're going to take a look at a method called the false position method. And essentially, what we're going to do is we are going to find secant lines that go through 2 points of a function, and we're going to use that secant line to approximate the zero. So you can see this picture here. This would be the curve that we have. Okay, so this function f of x, and maybe we use this point A and this point B to construct a secant line that has the point A f at A and B f at B. And in a moment, I'll show you how this formula is arised. All right, but essentially, this is going to be the formula that we can use to rearrange the secant lines to get a new guess. Okay, and this x1 is going to be like a new guess. And then from there, what's going to happen is that's going to replace, and it's just going to keep guessing and guessing and guessing until eventually we get really close to the actual zero. Okay, so that's the whole purpose of doing something like this. Okay, just making some secant lines or deriving this formula. And just let me show you, just really quickly, not the entire formula's genesis, but for those of you that are interested, where this formula comes from. What you would want to do is you would want to just go ahead. Let me share again. Sorry about that. And let's say for some reason we have a function. All right, so I'm just going to draw it like this. Okay, clearly the zero is right here. And let's just pick this to be a point. Okay, and then let's pick another point, and I'm going to call this maybe the xu, the upper bound. And I'm going to pick a point that's equidistant from that point on the x-axis, maybe right here. Okay, and I'm going to get this. Okay, so this is going to be like our XL, our lower bound. Then I'm going to construct the secant line that goes through there. Now this is going to be our guess, and I'm going to call that XR, all right, to be able to approximate what the zero is going to be. And it's actually pretty close because this would be the actual zero right here. But what we can do is we can construct a triangle that looks something like this. Okay. And right here, this would be f at xl. Okay. And this point right here, this would be another triangle. Okay, if I were to construct it. So here and here. And I want you to notice that these triangles are similar triangles. Okay. And again, we have the distance. Okay. So, and I know I didn't do a good job with it, but just assume that this distance and this distance are the same. And so what that would say is that the f at xl, okay, which is the height, by similar triangle would be the same as fxu, which would be the height if this is fxu. So those would be similar. And then the distances would be similar. All right. So in other words, xr minus xl, and then xr minus xl as well. And then from using this relationship, what we could do is we could go ahead and just manipulate that. And eventually what happens is, I'm going to go back to the other screen, is that it just turns into this formula, okay, by just doing some manipulation. All right, so that's where the formula comes from. I'm not going to go through and derive the entire thing, but I think it's pretty easy to see. And so all we're going to do is we're just going to use this formula. And if this number is less than zero, then we replace the lower bound with this value. And this should be XR. I think that's a typo there. If XR is greater than zero, then we're just going to replace XU, the upper bound, with XR. And then if for some reason we get zero, well, then we're done because we've actually gotten the zero for this. And we're just going to repeat the process until the error is to some sort of desired value. All right, so realistically, folks, this is our formula. And then what we need to do is, in the meantime, we just need to figure out if the product is less than zero, then there must be some sort of zero in the interval still. Okay, so we just keep continuing the algorithm. All right, so realistically, this is just going to happen by default, so we don't even have to check that. So realistically, all we really have to check are these three conditions. All right, so let's go ahead and take a look at an example of this. And this is what we're going to do. Okay, and then the next video, probably what I'm going to do is, in this video, I'm probably going to do like the first few things of this, like maybe up to here. And then I'll do the actual false position method in the next video. All right, just because this stuff is actually pretty easy to do. So probably take us like maybe 5 minutes to do this stuff. So we have this function that we've been dealing with, e to the x minus 3. And we're going to write some MATLAB code to get a function from a user, plot it to get upper and lower bound. And then we're just going to get the lower and the upper bound from the user. And we're going to prompt them for an error, and then we're going to use our VPA solve function using the lower bound as the approximate. All right, so let's go ahead. We're going to CLC, we're going to clear all, and I'm going to define a sims x, right, to start with. All right, I'm going to go ahead and get the user of the function from the user, and I'm just going to call that R, all right, just because I can call it anything I want. And I'm going to say input, I'm going to say enter a function in terms of x. All right. And then what I'm going to do is I'm going to plot this. All right. So I'm just going to easy plot that function. All right. And then the other thing I probably want to do is I want to put the grid on for this. All right. So I think that's realistically the first two parts of what we're asked to do here. So we want to prompt, and then we want to plot. Then we want to get an upper and lower bound. Okay. So I'll just call that high and low to make it easy. So we'll go back to MATLAB. So I'm going to say low, and I'm going to get that from the user. And I'm going to say enter a lower bound. And then I'm going to go ahead and say for high, I'll just copy and paste this. And I'm going to say enter an upper bound. All right. Right. And then once I have that, I'm going to get the error from the user. I'm going to call that U error. Okay, so U error is going to be input. And we're going to say enter an error to approximate the 0, 2. Okay. And then the last thing I'm going to do is I'm going to VPA solve this equation for 0, right? I'm going to approximate the 0 for that. So I'm just going to say, I'm going to call that actual. And I know that doesn't make sense because we can't really get an actual solution, but it's probably going to be as close as we can get. And I'm going to say VPA solve. And I'm going to say R double equals 0. I'm going to solve that for X. And then the approximate I'm going to use is the lower bound. Okay, so if we look at what the instructions were, remember it says use the VPA solve, use the lower bound as the solution. And I'm going to use that as the quote unquote actual value. All right, so that's all like the prerequisite stuff for this. Okay, so I'm going to say that it's going to be low. All right, and let me go ahead. I'm just going to leave this unsuppressed, but I'm just going to go ahead and run this to show you what happens, and hopefully I didn't make any syntax errors. All right, so I'm going to enter the function. So exp of x minus 3, I think was the function that we're testing with. And then what it's going to do is it should plot over here. We can zoom in, and I believe that we've used 1 and 2 as like a pretty good indicator for this. I may or may not have said use certain parameters for this, but it looks like I said use 1 and 2 for the test case. So let's go ahead and do that. So my lower bound, I'm going to use 1, and my upper bound is 2. And then I'll just say 0.01. And then this is going to be the actual value, about 1.5. And if we kept zooming in, we could clearly see that 1.5 is a really good guess for our 0. Okay, so at least that makes sense. All right, so now that I've gone through and kind of plotted like the prerequisite stuff, what I'm going to do is I'm going to stop this video. And then the next video, what I'm going to do is I'm going to really focus on how to derive the false position algorithm. Okay, at least code that algorithm in MATLAB. And then also to print the table. All right, so that way it's in a nice, neat format. And we can kind of use this for our assignment sort of basis.